Hello, I am Gopakumar. Welcome to your math tutor. Here we focus on helping you to solve the problems in engineering mathematics in the easiest possible way from an exam point of view. If you are interested in theory, then check out NPTEL.
Diagonalize the matrix A is equal to two, 1, minus 1, 1, 1, minus 2, minus 1, minus 2, 1. By means of similarity transformation. Hence, find a raised to 4.
Diagonalize the matrix A equal to 2, 1, minus 1. Second row is 1, 1, minus 2. Third row is minus 1, minus 2, 1. Diagonalization can be done by orthogonal transformation and similarity transformation. To do orthogonal transformation, the matrix have to be real symmetric. For a matrix to be symmetric, the transpose of the matrix A should be equal to matrix A itself. Here the rows of matrix A are color coded. This is for you to easily understand how the transpose of the matrix is done. Here we have matrix A. To write the transpose of the matrix, write the first row as first column and second row as second column and third row as third column. As you can see here, A and A transpose are same. Therefore, the given matrix is symmetric. Since the matrix is symmetric, we can diagonalize the matrix using orthogonal transformation. First of all, we have to find the characteristic equation. Characteristic equation is mod A minus lambda I equal to 0. Subtract lambda from leading diagonal elements. Then result of A minus lambda I becomes mod 2 minus lambda one minus 1 1 1 minus lambda minus 2 minus 1 minus 2 1 minus lambda equal to 0. Normal method to obtain the characteristic equation is to take the determinant of A minus lambda I. But here we are using another method which saves a lot of time. General form of characteristic equation can be written as lambda cube minus d1 lambda square plus d2 lambda minus d3 equal to 0. Here d1 is the sum of diagonal elements. Therefore, d1 equal to 2 plus 1 plus 1 equal to 4. d2 is the sum of minors of the leading diagonal elements. first diagonal element is 2, and just ignore the elements in the first row and first column of the matrix. The rest of the elements form the minor of the leading diagonal element 2. That is mod 1 minus 2 minus 2 1 plus the next diagonal element is 1, and ignoring the elements in the second row and second column, the rest of the elements form the minors of the leading diagonal elements 1. That is 2 minus 1 minus 1 and 1 plus last diagonal element is 1. Ignoring the elements in the third row and third column, the rest of the elements form the minors of the leading diagonal element 1. That is mod 2 1 and 1 1. After cross multiplying the terms, we get 1 minus 4 plus 2 minus 1 plus 2 minus 1, which is equal to minus 3 plus 1 plus 1 equal to minus 1. D3 equal to determinant of A. Determinant of a 3 by 3 matrix is given by A11 into minor of A11. Here A11 is 2 and minor of A11 is mod 1 minus 2 minus 2 1 minus A12 into minor of A12 here A12 is 1 and minor of A12 is 1 minus 2 minus 1 1 plus A13 into minor of A13. Here A13 is minus 1 and minor of A13 is 1, 1, minus 1, minus 2. Let us cross multiply the terms inside the minus. Then the equation becomes 2 into 1 minus 4 minus 1 into 1 minus 2 minus 1 into minus 2 plus 1. 2 into 1 minus 4 is minus 3, minus 1 minus 2 is minus 1, minus 1 into minus 2 plus 1 is minus 1, which is equal to minus 4. We know that the characteristic equation is lambda cube minus d1 lambda square plus d2 lambda minus d3 equal to 0. Substituting the values of d1, d2, d3 in the equation, we get lambda cube minus 4 lambda square minus lambda plus 4 equal to 0. In the equation, lambda cube minus 4 lambda square minus lambda plus 4 equal to 0. Degree is 3. This means that the equation will have 3 roots. The 4 here is the product of those 3 roots. The factors of 4 is 1, 2 and 4. For solving the equation using trial and error method, put the value of lambda as plus or minus 1 or plus or minus 2 or plus or minus 4. Put lambda is equal to 1 in characteristic equation. Then lambda cube minus 4 lambda square minus lambda plus 4 equal to 0 becomes 1 cube minus 4 into 1 square minus 1 plus 4, which is equal to 1 plus 4 is 5 minus 4 minus 1 equal to minus 5, which is equal to 0. Therefore, lambda is an eigenvalue. For finding the other 2 eigenvalues, we have to factorize the equation. For that, we use synthetic division method. The characteristic equation is lambda cube minus 4 lambda square minus lambda plus 4 equal to 0. coefficient of the characteristic equation is written down. Coefficient of lambda cube is 1. Coefficient of lambda square is -4. Coefficient of lambda is -1. Plus 4. We take the divisor as 1 since lambda equal to 1. One is brought down and 1 is multiplied with divisor, and the result is written below -4, adding -4 plus 1, which is equal to -3. Again -3 is multiplied with 1, and the result is -3 is and we write it below -1 and add -1 and -3, we get -4, and again multiply -4 with 1, we get the result as -4, which is written below +4, and add -4 plus 4, we get the result 0. Now we have second degree polynomial after division. Lambda square minus 3 lambda minus 4 equal to 0. On further factorizing, lambda square minus 3 lambda minus 4 equal to 0, we get the factors as lambda minus 4 into lambda plus 1 equal to 0. Then we get the result lambda equal to 4 and lambda equal to -1. Consider lambda equal to 1 as case 1. Subtract the value of lambda from diagonal elements of matrix A. Then we get the matrix as first row as 1 1 -1, and the second row is 1 0 -2, and third row is -1 -2 0 into x1 x2 x3 equal to. 0. Here x1, x2, x3 forms the eigenvector. For finding the value of x1, x2, x3, use the following method. x1 by minor of a11. Here a minor of a11 is 0 minus 2 minus 2 0, and cross multiplying we get 0 minus 4 equal to minus x2 by minor of a12. Here minor of a12 is 1 minus 2 minus 1 0, and cross multiplying we get 0 minus 2 equal to x3 by minor of a13. Minor of a13 is 1 0 minus 1 minus 2, and cross multiplying the minus 2 plus 0. Eliminating common factor minus 2 from denominator, then we get x1 by 2 equal to x2 by minus 1 equal to x3 by 1. That gives the vector x1 equal to 2 minus 1 1. 2 minus 1 1 is the eigenvector corresponding to lambda equal to 1. Now consider the case lambda equal to 4. Subtract the value of lambda from diagonal elements of the matrix A. Then we get the matrix as minus 2, 1, minus 1, and the second row is 1, minus 3, minus 2, and the third row is minus 1, minus 2, minus 3 into x1, x2, x3 equal to 0. Minor of a11. Here minor of a11 is minus 3, minus 2, minus 2, minus 3, and cross multiplying we get 9 minus 4 equal to minus x2 by minor of a12. Here minor of a12 is 1 minus 2 minus 1 minus 3, and cross multiplying minus 3 minus 2 equal to x3 by minor of a13. Here minor of a13 is 1 minus 3 minus 1 minus 2, and cross multiplying we get minus 2 minus 3. That is equal to x1 by 5, x2 by 5, x3 by minus 5. Eliminating common factor 5 from denominator, we get x1 by 1, x2 by 1, x3 by minus 1. That gives the vector x2 as 1, 1, minus 1. Then 1, 1, minus 1 is the eigenvector corresponding to lambda is equal to 4. Lambda equal to minus, subtract the value of lambda from we get the matrix as 3 minus 1 and the second row as 1, 2, minus 2. And the third row is minus 1, minus 2, 2 into x1, x2, x3 equal to 0. x1 by minor of a11. Here minor of a11 is 2 minus 2 minus 2, 2, and cross multiplying we get 4 minus 4 equal to minus x2 by minor of a12. Minor of a12 is 1 minus 2 minus 1, 2, and cross multiplying we get 2 minus 2 equal to x3 by minor of a13. The minor of a13 is 1, 2, minus 1, minus 2, and cross multiplying we get minus 2 plus 2. That gives x1 by 0, x2 by 0, x3 by 0. This method fails because all the elements in the denominator are 0. Since the second and third row are identical, method fails. Therefore, we have to take a pair of rows which are not identical. So, in this case, we take row 1 and row 2. Instead of x1 by minor of a11, we take x1 by minor of a31. Here the minor of a31 is 1 minus 1, 2 minus 2, and after cross multiplying we get minus 2 plus 2 equal to minus x2 by minus of A31. Here the minor of A32 is 3 minus 1, 1 minus 2, and after cross multiplying we get minus 6 plus 1 and equal to x3 by minor of A33 Here the minor of A33 is 3112, and after cross multiplying we get 6 minus 1, which is equal to x1 by 0 equal to x2 by 5, x3 by 5. Eliminating common factor 5 from denominator, we get x1 by 0 equal to x2 by 1 equal to x3 by 1. That gives the vector x3 is equal to 0, 1, 1. Zero, 1, 1 is the eigenvector corresponding to lambda equal to minus 1. X1 is the eigenvector corresponding to lambda equal to 1. And x2 is the eigenvector corresponding to lambda equal to 4. And x3 is the eigenvector corresponding to lambda equal to minus 1. Eigenvectors x1 and x2, x3 form the modal matrix. Then vector x1 becomes column 1 and vector x2 becomes column 2. Vector x3 becomes column 3 of the modal matrix. Now to diagonalize the matrix by similarity transformation, use the formula D is equal to M inverse AM. To find M inverse, find determinant of M and cofactors. Determinant of M is equal to A11 into minor of A11. Here A11 is 2, and after multiplying the minor of A11 we get 1 plus 1, and minus of A12 into minor of A12. Here A12 is minus 1, and after multiplying minor of A12 we get minus 1 minus 1 plus A13 into minor of A13.
Here A13 is 0, and after cross multiplying minus of A13 we get 1 minus 1. Therefore, determinant of m equal to 6. Cofactor of A11. The minor of A11 is 1 minus 1. After cross multiplying we get 1 minus 1, which is equal to 2. Cofactor of A12 is negative of minor A12. Here the minor of A12 is minus 1, 1, 1, 1. After cross multiplying the minus we get the cofactor A12 as minus of minus 1, which is equal to 2. Cofactor of A13. Here minor of A13 is minus 1, 1, 1, minus 1. After cross multiplying the minus we get 1 minus 1, which is equal to 0. Cofactor of A21 is negative of minor of A21. Here the minor of A21 is 1, 0, minus 1, 1. After cross multiplying we get the cofactor of A12 as negative of 1 plus 0, which is equal to negative 1. Cofactor of A22. Here the minor of A22 is 2, 0, 1, 1. After cross multiplying we get cofactor of A22 as 2 minus 0, which is equal to 2. Cofactor of A23 is negative of minor A23. Here minor of A23 is 2, 1, 1, minus 1. After cross multiplying we get the cofactor of A23 as negative of minus 2, minus 1, which is equal to 3. Cofactor of A31. Here the minor of A31 is 1, 0, 1, 1. After cross multiplying we get cofactor of A31 as 1 minus 0, which is equal to 1. cofactor of A32 is negative of minor A32. Here the minor of A32 is 2, 0, minus 1, 1. After cross multiplying, we get the cofactor of A32 as negative of 2 minus 0, which is equal to minus 2. Cofactor of A33, here the minor of A33 is 2, 1, minus 1, 1. After cross multiplying, we get cofactor of A33 as 2 plus 1, which is equal to 3. Adjoint of model matrix is the transpose of the cofactor matrix. Therefore, adjoint of model matrix equal to 2, 2, 0, minus 1, 2, 3, 1, minus 2, 3. Inverse of model matrix is equal to adjoint of model matrix by determinant of model matrix. Determinant of model matrix is 6 into adjoint of M is 2 minus 1, 1, 2, 2, minus 2, 0, 3, 3. Multiplying it with 1 by 6, then we get 1 by 3 minus 1 by 6, 1 by 6, 1 by 3, 1 by 3, minus 1 by 3, 0, 1 by 2, 1 by 2. Now to diagonalize the matrix by using similarity transformation, use the formula D is equal to M inverse AM. Where M inverse is the inverse of model matrix and A is the given matrix, M is the model matrix. After multiplying these three matrices, we get diagonalized matrix D equal to 1, 0, 0, 0, 4, 0, 0, 0, minus 1. The most important thing you have to understand here is, for every diagonalized matrix, the principal diagonal elements will be eigenvalues of the given matrix. All other elements except leading diagonal elements will be 0. Now to find a raised to 4, use the formula m d raised to 4 M inverse. M is the modal matrix 2, 1, 0, minus 1, 1, 1, 1, minus 1, 1. D raised to 4 is equal to 1 power 4 equal to 1, 0, 0, 0, 4 power 4 equal to 256, 0, 0, 0, minus 1 whole raised to 4 equal to 1. Inverse of modal matrix is 1 by 3 minus 1 by 6, 1 by 6, 1 by 3, 1 by 3, minus 1 by 3, 0, 1 by 2, 1 by 2, after multiplying these three matrices, we get a raised to 4 equal to 86, 85, minus 85, 85, 86, minus 85, minus 85, minus 85, 86.